Alright, hey everyone, I'm going to be running through all of the questions that we didn't get through in this discussion, and so I'm going to have like all of the questions here, so if you like want to go over like a specific one, feel free to like skip around. But yeah, let's start off with question number 1, so paths list. And so here, we're trying to like return like a list of ways to reach, like we're given two numbers x and y, and we can either like increment it by 1 or like double it, and we want to return like list of all like the different paths we can take. And so for example, I'll draw out like the longer one, so 3 and 9. And so if you might imagine, what's going to happen is that we can go from 3 plus 1 plus 1 plus 1 plus 1 plus 1 all the way to 9. And so that's like going from 3, 4, 5, 6, etc. to 9. That's one path. Another path that we can take is like 3, 4, 8, 9. So like plus 1 times 2 plus 1. Another path is, let's say, 3, 6, 7, 8, 9. So like 3 times 2 plus 1 plus 1 plus 1, 6, 7, 8, 9. And as you can see, it's like returned as a list right here of like all of these 3 different paths. And then so what we want to do is like take a look at the skeleton code that I have so far. And so a couple things that we can note is that we have like 2 if cases right here. And it's like if something, return something, elif something, then return something. And that gives the idea that, you know, it might be a base case, because typically whenever you see like if condition and like a return, that's like usually checking for like some condition before you like immediately stop the program, and like before it goes into like maybe a recursive call. And we can also see that it's like probably going to be a recursion, because there's this idea of that we want to get to like y by either like incrementing or doubling. And so we have like these 2 different choices. So as a matter of fact, it might be like tree recursion, because we have 2 different choices to like branch off of. For example, we can go like plus 1, so increment, and then from increment we can like branch off into like incrementing or doubling. So like we could go like any combination of like plus 1 or times 2. And so yeah, let's start by maybe diving into like the recursive call. And so the idea here is that we can have like 2 different options. We could have the option of maybe like let's say incrementing it or doubling it. And so let's start off with maybe 3, and we're going to branch off into 4 and then 6. And then so the thing is that let's say we're trying to get to maybe the number 6, and so we have like a 6 right here, and if you imagine this 4 is going to branch off into like a 5, maybe double it, so it goes to 8. And yeah, I'll like finish like drawing this tree out maybe. And there are like a couple of things that we want to know. And so one thing we want to know is that the 2 choices that we have are always going to like increase the number. And so incrementing is going to add 1 to it, that's going to increase it, and doubling is going to add like always like increase it, because they're all positive integers. And so because of this, once we've like passed the number that we're trying to like get to, for example, like this y number, in this case, we're trying to get to the number 6. Once we pass that number, there's no way to go back. And so if our number is maybe x, and we're trying to get to y, but x is greater than y, then there should be no paths, because we can't go like backwards. And so looking at like the 8, looking at the 10, these are like sort of the conditions in which, you know, we have no paths. And if we have no paths, you know, our return result is going to be a list of paths. And so since we have no paths, we're going to want to like return an empty list. And so we can like code it up here. If y is greater than x, if x is greater than y, because we're trying to go from x to y, we're going to return an empty list, because there are no paths and there's no way for x to reach y. But let's consider like another case, right? And so another case would be like this 6 right here. And so what we want to notice about that is that x has already hit y. And because there's no like point in like incrementing or doubling, because if we like increment it, it's going to go past 6 to 7, and we can't really go back from 7 to 6. If we double it, we can't really go back either. So that's where we want to stop, because there's like no point in incrementing or doubling it. And we have one path exactly. And what that one path is going to be where we like only have the number 6. So 6 is the last number, and we're going to like return that. And if we notice right here, the doc tests are like always like pretty useful for like determining like base cases. And if we see like paths of 3, 3, is going to return exactly one path, and that's going to be the number 3, because that's the last element in the sequence, and like that's the only element because we're not like incrementing or doubling it any further. And so that's going to be like another base case, and that's going to be if x is equal to y. So if like this 3 is equal to 3, we're going to return one path, like a list containing one path, and that path is going to contain just the number whatever y is. Or you could put like x or y because they're both equal, but yeah, one path with that number. And yeah, so we got the base cases down, and like let's maybe look into the recursive call. And so a couple things that we want to note is that let's like ignore all of these down here, and let's only consider like this part right here. And let's imagine like the recursive calls that this 3 node is trying to make. And so we make a call to like paths of 4, 6, and we make a call to like paths of 6, 6. And we already know that like path of 6, 6 is going to return list 6, because list of the path with 6 in it, because that's the only like we already like coded that base case in. But another thing we want to note is that for paths of 4, 6, well, let's think about like the ways to get there. And so if we think about it, 4 goes to 8. That's already past 6, so that really doesn't count as a path. So the only path that we're going to have is we're going to be incrementing it. So the path is going to be from 4 to 5 and 6, so like adding 1 each time. There's only one path. And the result that we want to get out of this is, if we notice right here, this list 3, 4, 5, 6, and the list 3, 6. And we see that like from 3 we can only get to 6, and we can only get to 4. And from each of these things we went to, so we like, let's say we increment to 4, we like get back like a certain amount of paths that we can have. So in this case, from 4 to 6, we have the path 4, 5, 6. And then from 6 to 6, we have just the path 6. And what we can do with this is that we can add this 3 back in. And so 3, if we like add 3 to like 4, 5, 6, we get like the path like 3, 4, 5, 6. And if we like add like 3 plus 6, right here, we get like a path 3, 6. And so what we're going to do is we're going to branch off into like 2 different paths, so like incrementing or doubling. And we're going to take those recursive calls, and those recursive calls, if you might imagine, like the recursive leap of faith, they're going to give back like the paths from that number to whatever y we're trying to reach. And then once we get those paths, we can add like the 3 back in, and that's going to be like our total amount of paths. And so that's probably what like the A and B are going to be, because we have 2 options, and in this case we have like 2 variable assignments. So let's start with 8, and let's say A is going to be like incrementing. We could like, it can be in any order. Let's just say it's like when we're adding 1 to it. And so we're going to say that this is going to be a recursive call to x plus 1, paths of x plus 1 and y. So we're incrementing 1, and then for B, it's going to be paths of x times 2, y. And then so what this represents is that the increment is going to correspond to paths of 4, 6. Oh, I just realized I wrote where my face is, but hopefully that it goes to like the list 3, 6 right here. Yeah, and then this is going to be the path where we like double it. And what do we want to do? We want to add both of these lists together, and in addition to that, we want to add like the current like number that we're currently at. So in this case x, we want to add it to every single path in like A and B. And considering how we only have 1 line, we want to do this through a list comprehension, because we're going through each element and we're adding something to like the beginning of each element. And then, so we're going to have some expression for something in something, probably. And we might add some additional stuff, but yeah. And so what we want to add 3 to the beginning of is every single element in both A and B. And because we want to add it to like elements in both A and B, we're going to go A plus B. Because we're adding like the list paths of 4, 6 and paths of 6, 6 into like the list, conjoined list of like 4, 5, 6 as one path and the list 6 as another. And we're going to add the 3 to the beginning of each of them. And then let's call this variable path. So each variable is going to be like a different path. For example, it might be like 4, 5, 6. Another time it might be like the list 6. And what do we want to add to it? We want to add like the current value x to it. So it's going to be x plus path for path in a plus b. And if we run it, let's see. Hopefully I didn't mess up. Okay, all right, it works. Yeah. So just like reiterate, what's going to happen is that we're going to make a recursive call. One is going to be, what if we increment x by 1? And the other recursive call is, what if we multiply x by 2? And then each of those recursive calls is going to return like a list of different paths from that certain number. And then what we can do with those like paths is that we can add x to the beginning of it, and we get like the path from x to y. Because like what's going to happen is that we're going to get like paths from like x plus 1 to y, and we're going to have like x times 2 to y. And what we can do is that we can add this like x in. So x, the path from x to x plus 1 to x to y is equivalent to from a path from x to y. And so joining all of these together, we're going to get our answer right here. And yeah, all right, let's move on to question number 2. And so you probably won't see like a variation of this on the exam, because I think a lot of the exam questions are like skeleton code. But so this is like pretty freeform, but mutation is like worth remembering. And so we're going to reverse the given list, and so we're not allowed to use like a reverse function. I think it's called like list.reverse or something, and it like reverses it for you. But yeah, so if we notice right here, we have the list like 5, -1, 29, 0. And if we reverse it, what's going to happen is that 0, the last element, is going to be first, 5, the first element, is going to be last, and etc. And so yeah, and one thing to know about this is pretty useful for a lot of exams is that they don't tell you, usually don't tell you like directly, you're going to mutate the list. Actually, they do tell you, but in the doc test you can always like see if it's like mutation or non-mutative. And so in the case of right here, we define an original list, and then we call reverse, but we don't actually like assign it to a variable. But what we notice after is that original list has changed. So we didn't like reassign original list, but we called a function and it somehow changed. So that's going to be like a mutated function. But yeah, and so the idea here is that we want to swap like the 0th element with like the last element, and the first element with like the last -1th element, and like the second with the last -2th element, and etc. And so up to like some certain number, so like nth and the last -nth number. And what is this last number exactly? Well, it's going to be like the length of list -1, or you could code it up as -1, either way. So like -1 represents like the last number, length of the list -1 is also like the last number. So whatever like the 0 is right here. And we want to swap it until like some certain point. And what is that point? Well, we want to swap it until we're like halfway. And so we want to swap the 0 and the 5, and then we move on. We want to swap the 29 and the -1. But we want to stop right there because we don't want to like to swap these like again, because they're going to like go back to their original position. And so to be exact, we're going to swap it length of the list divided by 2 times. Because like let's say we had like an odd numbered list, and so the length is 3. If we floor division it by 2, it's going to become 1. And so that means we want to swap like the 1 and 3, and then we don't swap the 2. And if we have like even list, like 1, 2, 3, 4, and 4 divided by 2 is going to be 2. We want to swap the 1 with the 4, we want to swap the 2 with the 3, and then we want to stop there. So we only want to do like the length of the list divided by 2 number of swaps. And in particular, how do we like swap these numbers? Well, how are we going to do it? And this is like pretty typical with like mutation in general, is that along with like methods such as like append, extend, in this case, we're not like adding elements or like extending elements or things like that. We're swapping elements. So to swap them, we're going to do like let's say we want to swap like elements I and elements j. We're going to do that by doing list of I, so like the ith element and the jth element, they're going to be swapped with each other. So the ith element is going to become the jth element, and the jth element is going to become the ith element. And so that's how we're going to do it. And so we're swapping numbers up to like this length of the list divided by 2 element. So we're probably going to have like a for loop. And so for I in range of the length of the list divided by 2. And so it's going to go like 0 to 1 to 2, all the way to like the length of the list divided by 2. And what are we going to do here? We're going to swap the ith element, and so the 0th element maybe, with like the last element of the list. And so you can do this as like the length of the list minus 1. And so that's going to be like the last element, but you need to also subtract by I. And the reason behind this is that if we like think about it, the 0th element is going to correspond to like the length of the list minus 1. That element, actually, it might be more clear to write it like this. So the 0th element is going to be swapped with like a -1th element, or the last element. And the first element is going to be swapped with the second and last element. So like the second element is going to be swapped with the second to last. The third element is going to be swapped with the third to last, and etc. And so yeah. So in addition, we're going to replace j with -1 minus I. It's like the ith last element. And yeah, we should be done here, hopefully. Maybe I forgot something. But let's run the test. And yeah, so this is going to be reverse list. So we're going through like each element of the list, swapping it with like the first element with like the last element. I compared to like -1 minus I. We're swapping those two until we get like halfway through the list. And yeah, let's see. All right, question number 3. So trees, and this is going to be the function reverse other. And so what we're going to do here, I'll draw it out, is that we're going to have a tree. And let's say this is like way too big for me to like visualize, so I'll make up my own example. It's like 1, 2, 3, and then 4, 5, 6, 7. And so what's going to happen here is we're going to mutate the tree. So note that it's a mutative function, not a non-mutative one. And we're going to mutate it so that like nodes on every other odd def, we're going to reverse the labels of all their branches. And so what we're going to do is, this is an odd def. This is like def 1. And so what we're going to do here is we're going to reverse all the labels of the branches. And so I want to make a copy right here, just like visualize like how it changes. And so what's going to happen is we're going to switch like the 3 and the 2. And so it's going to become like 2, 3, 2. And then if we go to like all the branches, I'll like draw this all out. Note that like the def is 2 right here. And since it's even, we don't really care about like reversing their branches. And so we can like go further down. And if we go to this list down here, 5, it's an odd def branch, but it doesn't have any odd def like tree, but it doesn't have any branches. And so we don't really have to do anything because we can't like reverse like no branches. And so let's skip that. And then we see the 4, 6, 7, and we know that 4 is odd def. And so we're going to reverse the 6 and the 7, and we get like 7 and the 6. And then we're going to recurse down. We're going to hit like def 4, and 7 and 6. They don't really have any branches, so there's nothing to do here. And anyways, it's also odd, like it's also an even def tree, so we don't really care about that either. So yeah, let's maybe dive into like the code a little bit. And so as with like all like tree problems pretty much, we're gonna be dealing with like tree recursion. And so the idea here is that like we might do something with current node and then recurse on branches. And so like recursive B for B in branches, T dot branches. And so we're gonna do something like at the current like def of the tree, and then we're gonna make a recursive call on each of the branches. And what's gonna happen is that typically we're going to recurse all the way down until we hit like the base case. So if t is leaf do nothing. And so yeah, so let's think about like what variables we kind of need. And so we're gonna have like the tree, and we're gonna make a recursive call to like b. But the question is here, how are we gonna know if like the tree is an odd def? And if we just like make a call to like recursive of b, it's like call to the branch, we don't really know if it's going to be like an odd def tree. Because like, let's say we make a recursive call on this tree right here from like the original tree with 1, and we make a recursive call on this like 2 tree right here. We're only past the tree, but we don't know if it's like odd def or even def, so we're gonna have to like, we don't really know. So because of that, we're gonna have to add like an extra variable that's going to tell us, is this odd tree, is it like the current tree or branch that we're at, is it odd def or is it even def? And so we have this idea of like adding an extra parameter. And so because of that, we probably need a helper function. And so this is actually going to be a higher order function mixed with like a tree recursion problem. And so we're going to call this function maybe like helper. And we're going to have like a parameter t. So like t is the tree that we're currently passing in. But we also need a variable like is odd. And so we added this extra parameter, and we're going to like do all of the logic that we had, like swapping the branches, recursing on the branches, and etc. And then at the very end, we're going to like make a call to helper. And let's think about like what this call to helper is going to be. Well, we want to pass in the current tree because the purpose of helper is only to add an extra parameter, like is odd. And the question is like, what is odd? Well, let's say like the is odd variable like says whether we're at like a odd def or even def. And since we're starting at the very top, it's like the one at the very top, that counts like as an odd def tree. And because of that, we're going to pass in true. So is odd is going to be true because we're starting at def 1. And then, yeah, let's go into like this helper function, which is, And so let's start with like doing something with the current node. And so the thing about this is that we only want to do something if the tree is like at odd depth. And so we're going to check, is it odd? And if it is odd, then what do we want to do? We want to reverse all of the labels. And so let's say we're going to call like a variable reverse labels. And first of all, how do we get all the labels? And so we have t.branches, and that's going to be like a list of trees. And then we want the label from each of them. And so we're going to have a list comprehension. And so something for b in t.branches. And so we're going through each like branch, and we want to get the label of it. And we're going to do that via like b.label. And so we got a list of all like branches, and that might be like the list like 2, 3, if we're like calling it on the one tree. And how do we reverse it? Well, we can reverse it using like this function right here. We could like create the list like reverse labels, and we could call like reverse labels. But one kind of neat way to do it is by list splicing. And so I'll just like put this right here. And so what's going to happen is that, to be honest, you don't need to like remember this like too much. But what happens here is that it's like an implicit, so list comprehension can be like split, like list splicing can be split into like 3 different parts. So start to end to like the step size. And if you don't specify, like normally you're going to only have like start to end, or like start to colon, or colon end. But in this case, what happens is that it's by default going to be from 0 to the end, so to the length of the list. And it's going to be like step size -1. So it's going to go from, actually it's going to go from like length of the list to 0 with the step size of -1. And so what's going to happen is it's going to go like reverse the list. But yeah. And so after that, we got like all the reverse labels, and what do we want to do? And so what we want to do is we want to go through like each branch and like get the corresponding label that we should have. And so it's already reversed for us. So what we want to do, we want to go for I in range of like the branches. So we're going through each of the branches, and we want to set like t dot branches of that I. So we're getting the ith branch, and we just want to set the label to be like the ith element of reverse labels. So what this corresponds to is that we have like the reverse list, like 3, 2, and then we're going through each tree. So corresponding right here, the 0th I0, we're going to get the ith element of the reverse labels, which is 3, and we're going to set it to be equal to 3. And we're going to go to the next one. We're going to set that to be like the first element, which is 2, right there. And that's going to be how we're going to reverse our list. And then after we have all of that, we're done with like doing things to like the current node. And so once we do that, we're kind of done here. And what we want to do is we want to make a recursive call on each of the branches. So we're going to go for b and t.branches, and we want to make a recursive call on each of them. So we're calling helper on every single one of them. And so helper b, and then what's the other parameter that we want to pass in? Well, the thing is, if we're moving from an odd branch to an even branch, we want to indicate that, it's an even branch now. And so if it was true, it should be false. So odd goes from even goes from odd. And if it was false originally, we want it to turn into true. So we're going to go helper of b, the next branch, and we're going to switch whether it's like even or odd. So not is odd. And yeah, that should be all of reverse other, and let's see if it works or not. Right, yeah, nice. And so just to reiterate, typically with like tree recursion, we're going to do things like the current node. In this case, if it was odd, we reverse all the labels of the branches. If it isn't, then we keep on going. And then we're going to like switch up whether it's even or odd, and we're going to make a recursive call on each of the branches. And yeah, and in this case, remember that if you need an extra variable, you might need a helper function. And you can usually see if you need like a helper function with like the skeleton code. And yeah, moving on to linked list, we're going to have a function called deepMap, and it's going to take in a function f and a link. And I think you might have done this in like lab or homework with like a regular list already, but here we're doing it with like a linked list. And so the idea is like pretty similar. And so let's say our linked list, I'm going to draw an environment diagram, sort of, so like the box and pointers. And let's say our linked list is like maybe this thing right here. And so what we want to notice is that it's going to be a non-mutative function right here. And so we're going to be applying fn to each of its elements, like mapping it. And so what's going to happen is that, we create s to be like a link of like 1, 2, 3. Let's use my example actually. And then if we call like deepMap, we're going to pass in a function called like square on this linked list. And then the return result should be 1 squared, and the list like 2 squared, 3 squared. And actually, let's fit it to the actual doc test. So it's going to be like a linked list 4 right there. And then it should also be like 4 squared. So it's like 1, 4, 9, 16. And yeah, so another thing to note is that this is actually going to be like a non-mutative function. And so earlier I said that like if you don't see like a variable assignment and they like it changes, it's going to be like a mutative function. But in this case, what they're doing is they're calling deepMap, which is going to return something, and they're printing it out. And so if you might imagine, if it was like a not mutative function, what would happen is that deep map would return like none, because mutative functions typically don't have like return values. And if you print none, nothing's gonna get printed out. But since like they called it and it printed something out, like an entire object, that means like deep map is returning a linked list, and so it's gonna be non-mutative. And if you notice right here also, print s does not change, so it's definitely gonna be non-mutative. And yeah, so the idea with like linked list, deep map with like list that you did in the lab, is that we're gonna go through each element. And so let's go through like each element of like this linked list right here. And so looking at the 1, we can directly apply fn of 1, and we're gonna get like some answer out of it, because fn, it should be applied on like integers or like numbers. And so we apply fn on 1 and we get something out, very cool. But then let's move on to like the next element. And then we see that it's a list, not a number. And with deep map, we want to go like deeper into it. And so what we're going to do is we're going to look inside this linked list, and we're going to see like a 2, we can apply fn on 2. We're going to see like list 3, we're going to apply fn on 3. And then yeah, and then we see the 4 as the last element, and we could apply like fn of 4. And if you might imagine, these like linked lists might go down like even further. And so what might happen is that this might be another linked list, and this might be another linked list, and it can go like infinitely down. And if it can go infinitely down and we want to handle like all of those cases, you probably want to do it like recursively, because recursion can like pretty much like go as far down as you want. And yeah, doing it iteratively can be like pretty hard. And so let's go through like each element. Like let's go through the linked list. And so what we want to check is whether we can like apply fn on the current element of the linked list that we're at. And if it does, we can like go on as normal, apply on everything else. But otherwise, we want to like go deeper down and make a recursive call. And so what we want to check here, we're going to use like the is instance variable function. And so if we check like if is instance of like link in this link object, it's going to tell us whether this link is actually like a link object or not. But what do we actually want to check? We want to check if the current element that we're at is going to be like a linked list. And so what we're going to do is we're going to check if is instance of link.first. And so link.first is the element that we're currently at, and link. So is it a link object? And the idea of like linked list typically is that we want to do something with the current element that we're at, so like link.first, and then move on to like the rest of the linked list. So like link.rest, and I'll comment it out here. Do something with link.first, current element. You can imagine this as like if it was like a regular list, the 0th index list, and then do something with link.rest, which is like list of 1 beyond. So everything except for the first element. And so what we're going to do is that we're going to check if it's like an instance of like link.first and link. And let's actually handle the case in which it isn't. So it's like not a linked list, and we can directly apply fn onto it. And so what we can do is we can apply fn on link.first. But then what do we want to do? We need to handle like the rest of the linked list. So we're going to make a recursive call. It's like deep map of f and link.rest. And so the idea here is that like, let's say we have a linked list with like a few elements. And so we apply fn onto this one right here, maybe. And then what we want to do is we want to make a recursive call for like the rest of the linked list. And so if you make a recursive call on the rest of the linked list, it's going to return like fn applied on the rest of the linked list. And what we can do is that we can like kind of like add this fn back in right here. And to add this fn back in, we're going to make a linked list out of it. And so we're making a linked list, where the first element is going to be fn, and then the rest is going to be pointing to like this recursive call of deep map. And so the first element is going to be fn applied on this current element, and the rest of the elements are going to be this recursive call on like link.rest. And so yeah, that's going to be handling the case in which it's not a linked list. Like the current element that we're at is not a linked list. So we're going to return that because this is a non-mutative function. And then else, what do we want to handle? We want to handle the case in which it is an instance of a linked list. And if it is an instance of a linked list, what do we want to do? We want to like recurse onto like that linked.first element. And if we can imagine, if we apply, like let me draw another example actually. So we have this linked list right here. And this is, the first element is going to be pointing to a linked list of the elements like 2 and 3. And then if we call deep map on this linked list, like the inner linked list, we're going to get like, and we use like the square function, we're going to get like 4, 9 out of it. And then if we call deep map on the rest, we're going to get like 16. And the result that we want out of it is going to be like a linked list with the first element being this like recursive call that we made on link.first, and the rest being the recursive call that we made on link.rest. It's like pretty much the same thing as like when it isn't a linked list, but replace like the fn of link.first with deep map of link.first. So we're making a recursive call on that linked list, and we're chaining it with the rest. So f of link.rest. And make sure to pass fn each time. And then yeah, and another thing to note is that we have a recursive calls right here, but we also need a base case. And so typically with linked list, our base case is going to be when we hit like a null, so like link.empty. And so, you know, we keep on like going through these elements. We're going to go to link.rest, 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 but then we hit like the end where link is link.empty. And then here, we should be returning link.empty. Because imagine, oh, shit. Imagine link.empty to be an empty list. Oh, where did my scratch go? Yeah, imagine link.rest to be an empty list, link.empty to be an empty list. And so if link is link.empty, so if there are no elements left, we're going to return link.empty. So we're going to be returning an empty list, and everything's going to like start off of here. Everything's going to build up from here. And yeah, this is going to be deep map, and let's run this, see if it works. Ooh, I messed up a bit. Oh, fn is not defined. This should be f. Alright, let's run it. And yeah. So just to reiterate, what's going to happen is that we're going to be applying f on the first element of the linked list. And there are like two scenarios. One, whether it is a linked list, like the current element is a linked list, or two, whether it isn't. And if it isn't actually, we're going to directly apply f onto that element and chain it with a recursive call to like the rest of the elements. Otherwise, we want to make a recursive call to that linked list, which is like the first element of the linked list. And then we're going to make a recursive call to like the rest and chain them together. And then the base case is going to be if we reach the end of the linked list. So if the link is empty, we're going to return link.empty. And yeah, right, let's move on to the last part. And so this is going to be SQL. And so we have question 9, big quarters. And I'm going to copy paste this right here. Actually, never mind. This is probably not very productive. Okay, yeah, it's not going to work. But yeah, so we're going to write a SQL statement, and it's going to select like a one column table of quarters in which more than 10 total points were scored. And so let's look at the tables that we currently have. And so we have a table called scoring, and we're going to have like a player, the amount of points and the amount of points they scored in like some certain quarter. And then you have like the players, and it's going to be like the player name corresponding to like which team they're on. So like Stanford or Cal. And let's think about like what we need to like get this like big quarters question. And so we're going to be selecting like a 1-column table of quarters, in which more than 10 total points were scored. And so the question is, do we like care about the players or the quarter, like, or the team that are on? And the answer is like no, we only care about like how many points were like scored in each quarter. And so we're probably not going to have anything to do with like this players table, only this scoring table right here. In addition, we have like a bunch of different quarters. And so let's think about like quarter one maybe. And if we think about it, quarter one, there's like 2 different players, and the sum of them is going to be 14. And so quarter one should be included in like the final table. And note that I thought about like the sum right here. So we have like a bunch of quarters. We want to group them together. So like quarter one, and we're summing all the like points from quarter one. It's like 7 plus 7, and we're seeing, is it more than 10? And keeping that in mind, you probably want to like group the scoring table by like the quarter, and like sum up the points and determine whether it's like greater than 10 or not. And so let's start that out. So select something from, I think, scoring. Yeah, select something from scoring. And in this case, you want to select the 1-column table of quarters. And so we want to select the quarter column, and so we're going to put quarter right here. And then what do we want to do here? We want to group by the quarter. And we're grouping by the quarter because we want to determine whether like the sum of the scores in each quarter are greater than 10. And so we're going to group by the quarter, and then we want to add having. So remember, if you want to like have like a where clause in which you want to deal with like the sum or like aggregation, so like sum, count, things like that, make sure to group by, and then put your like having clause. Like don't use a where clause, use a having clause, because having allows for like aggregation to happen, while like a where clause, you can't do like where sum greater than 10. You can't put like a where clause with like a sum. And so we're going to group by the quarter, and we're going to say having, what do we want? We want the sum of the points to be greater than 10. So we're selecting the quarter from the scoring table, and we're grouping it by quarter. So like quarter one, we're going to group these together, and we want to check, if their sum is greater than 10 of their points. And let's see, their sum of their points is like greater than 10, it's 14. And since it is greater than 14, we want to get a row that has like the quarter, and in this case it's going to be quarter one. So quarter one is going to be included in that table. And so let's paste it in here. And we're going to get quarters like 1 through 4. And so this is like a nice visualization. So we're going to group by the quarter that they're in. So like green corresponds to quarter 4, things like that. And so we group them based on quarter, and we're going to get the sum of each of them. And so the sum of this group is 7, which is not more than 10, so don't include that. This is 6, it's not greater than 10. This is 14, is greater than 10, so we want to include that. And this is like 17, is greater than 10, so we want to include that. And so these are like quarters 4 and 1. And if we go to the next part, we're going to get like quarters 1 and 4 out of it. And yeah, so that's going to be question number 9. And yeah, let's move on to question number 10. And so this is the last one, and we're going to have a SQL statement that's going to get a 2-column table. And so the first column is the team name, and the second column is like the total points scored by that team. And so yeah, so a couple things that we want to note is that the first column is going to be the team name, and the second column is going to be the points. So we have 2 different ideas of like team and points, and let's see where we can get that information. And so in the scoring table, we have like the points, and inside the player tables, we have the team. So we're definitely going to need like both the players table and the scoring table, because as you can see, there is no team column in like scoring, it only has points. And same with players, it only has team, it doesn't have points. So we're going to have to use both of those tables. And you might imagine that we're definitely going to have like from players and scoring. So we're definitely going to have these like two tables right there. And so in addition, we're going to have the team name, and we're going to have like the total points scored by that team. And keeping that in mind, we have like the idea of like total points. And the total points, we're going to be like adding together all like the players' points with that like certain, like belonging to that certain team. And that's going to be a sum. And so we're going to have like a sum. And because of that, we're definitely going to have like a group by something. And yeah, and we're going to have like a sum somewhere. And so the question is like, what are we going to group by? And so the first column is going to be like the team name and the total points scored by that team. So for each team, we're going to be like summing up all the points that they scored. So we're definitely going to be grouping by their team name. And so we're going to be grouping by their team. And what else do we want to do? And so we're going to be grouping by their team. And what columns do we want to select? Well, we want to select the team name, so team that we're grouping by, and we also want to get the sum out of it, and the sum of the points. And so we're getting the sum of the points as well as the team, but what else do we want to do? We want to make sure that that player we want to make sure that that player from the players table corresponds like the scoring table, because if we like aggregate these tables together, like players and scoring, it's going to make every single combination. So it's going to combine like Donald Stewart with Cameron Scarlett, every single combination, Donald Stewart with each one of these rows. But we want to make sure that Donald Stewart only corresponds to Donald Stewart and nothing else. And so because of that, we're going to have a where clause right here. And what's our where condition? We're going to make sure that the names of like the players and scoring are both the same. And so we're going to say where name equals player. And note right here that I don't have to do like players.name. Players.name equals like scoring.player, because it's unambiguous as like what table they're corresponding to. Because the player table, the scoring table doesn't have a name, and so we're saying that the name definitely matches to this players table right here. Because if you rename this player column as name, then you would have to say like player.name equals scoring.name, because they don't exactly know like which table this name belongs to. But in this case, name is unique. It's a unique column, so we don't have to say that. We can say like name equals players. But if you're like ever unsure, you can always just say players.name or something, because we definitely won't take points off for that. And so yeah, this is going to be the answer, and let's paste this in. And we get that Cal, the sum of their points is 24, Stanford is 20. And so let's run this through. And so we're going to join each of these together. And so we're going to be matching like so we're going to be like making every single combination of like players and scoring, but we want to filter out the ones only where they're equal to each other, like the names are equal to each other. And so if you notice, like Cameron Scarlett should not be with Chase Garbers, so we're going to add like the where clause, like where the name is equal to the player. And so if you can see, these all match up now, and we filtered everything out, and now we have all of these. And we want to group by their team. So Stanford, Stanford, Stanford. And so we have two groups, and we want to sum up all their points. It's like 7 plus 7 plus 3 plus 3. That's going to be 20 for Stanford, and for Cal, it's going to be 24. And so we're summing up all the points in each group, and we're going to get like the answer. So Cal scored 24, Stanford scored 20. And yeah, that's going to be all of the discussion that we did go over. And if you ever have any questions, feel free to like email me or post on Piazza. And yeah, all right, good luck on the final, and have a great night.